Alright, here to start us off, to introduce circular motion, we need to introduce Newtonian mechanics. So here we need to find some terminology. So mass is considered how much matter an object contains. Velocity is a relative vector quantity that has a speed and a direction component. And then momentum is just the mass times velocity. And this is a very useful quantity for analyzing physical situations. It's also important to note that momentum is a conserved quantity, so the change in momentum of your system has to equal the change in momentum of your surroundings. Some more terminology are forces, which is a quantification of an interaction between two objects. And then the net force is the summation of all the forces that act on one object. We also define something called the rate of change of momentum, which is a small change of momentum over a small time interval. So if you take this for a small enough time interval and a small enough change of momentum, you can turn it into a derivative, and that's called, you can say dp dt, which is a dp, so derivative of p with respect to t, and that's going to equal your net force. So that's a way you can equate a net force is acting on a system, and what that's going to do with the system is it's going to have a rate of change of its momentum if that net force is non-zero. So to clarify this some more, we also need to introduce Newton's three laws. And these are fundamental laws, and they have very, very important consequences on interactions between matter. And Newton's first law says, an object in motion tends to stay in motion, and an object in rest tends to stay at rest unless acted upon by an outside force. And it's very important to notice when it says acted upon by an outside force that it means a non-zero net force, because you can have a force acting on an object and you can have another force acting on the object, but if they're of the same magnitude and pointing in opposite directions, they'll cancel one another out and you'll get a zero net force, and then you won't have a change in rate of change in momentum, and the object's going to either stay at rest or stay in uniform motion like it was. So it is very important to distinct if there is a zero or a non-zero net force component and how this will affect the situation. Here's an example of such, and it's pretty much what I went through in the last slide. With you have, assuming the forces are balanced and you have the same forces on both systems, if an object at rest initially has zero velocity and you have a zero net force acting on it, then it means it's going to have zero acceleration because as you'll see with Newton's second law, how you can relate acceleration to force, so it's going to stay at rest. And same with the other side, except it's non-zero, but if acceleration is zero, then your velocity is not going to change, because the definition of acceleration is your change of velocity over change in time. So here with Newton's second law, it'll clear up that issue we had with relating force and acceleration. And this is stating the net force acting on an object is equal to its mass multiplied by its acceleration. So we're saying the net force and the acceleration point in the same direction, because that's very important to note because they're both vectors, and since mass is the only other object in the situation, it's a scalar, so all it affects is the magnitude of the two vectors, not the direction. So whatever direction the net force is pointing in is going to be the same direction the object is going to accelerate. And now this can be kind of a confusing concept for some students because they always picture, they don't look at what is happening beforehand. So they'll say if an object's moving to the right, per se, and then you apply a force to the left, a net force, non-zero to the left, it's going to decelerate it to the left. But the object's still going to move to the right for some point of time till it slows down, and then if that force keeps acting to the left, it then will go back to the left and start moving in that direction. So students sometimes have a hard time correlating. They think velocity is acceleration, and acceleration is rate of change of velocity. So it's a very, very important distinction. And here you just have the equation written quantitatively and then qualitatively. And then Newton's third law is for every action there is an equal and opposite reaction. And this is saying, in other words, forces acting on 1 by 2 is equal in magnitude but opposite in direction of the force acting on 2 by 1. This is often referred to as reciprocity, and it's basically just, it's kind of a perspective thing, so it's like relativity to an extent, where if you're looking at object 2 from object 1's perspective, you're saying it's acting on you with this force, but if you switch sides and you say, well, this one's acting on me in this way, and you're both correct in magnitude, but if it depends, the direction changes depending on which one you look at. And this is a very, very important quantity because if you know the one force acting on object 1 and you want to know the forces acting on object 2, you know it has to be equal and opposite, and you can just solve for it that way. And here it is again written in quantitative and qualitative manner. So now circular motion. So objects moving in uniform circular motion are experiencing a non-zero radially inward net force. And of course, we can now equate net force to acceleration at all times. So you can say the object is moving forward, so in whichever direction the object's moving, it's moving at that velocity as much as it's falling downward to the middle of the circle, which is why it moves in a circular pattern, is because it's moving to the right and down at any point in time as much as the same magnitude. So they end up with the superposition, and it goes in that circular motion. And later on, after I show you an example of this on paper, I will show you a YouTube video explaining circular motion more in depth. Alright, now here we're going to take a diagram here of, you could say, a comet orbiting a planet moving in circular motion, uniform circular motion. And we're going to calculate the rate of change of momentum at point A, B, C, and D. So here in this diagram, you have at point A, the red arrow is the acceleration, which is radially inward, and then the momentum is tangential, because it's pointing in that direction. And then it's the same at point B, C, and D. It just changes relatively. So now if we write out the equations for the force acting on A is going to equal the mass, assuming the mass doesn't change, we can keep it constant, times the acceleration at A and force at B, mass at A. So this is what I have so far. Pretty straightforward. And you do the same for C and D. As such. And going off of knowing just from vectors, since the mass here, since it is a scalar, and your only other two vectors are acceleration and force, then your force vector has to point in the same direction as your acceleration vector. So, since our acceleration is pointing radially inward, that means our force is pointing inward as well. And this is often what's considered the centripetal force. But don't confuse it with a real force, because it's actually a pseudo force, which is a fake force. What you really have, is it's the superposition of the gravitational force, which, depending where you are, say if this is your dot, and if this is on Earth, and then you define this as your standard XY plane, then at any point here, at point C, for example, you'd have the gravity force pointing downward, and you would have the frictional force pointing to the right. So since it's only at this exact moment there's no friction acting on it, then the upward force is the combination of the normal force opposing gravity and gravity, and it would look something like, if you draw the free body diagram of C, you'd have the normal force, and the force of gravity. You'd also have, so here you have the normal force and then the gravitational force, and you add these two real forces together to get this net force, or the centripetal force, which is equivalent to this force right here. So, and that's the same for each point along the circle. So that's how you come about getting the centripetal force. And now next, you'll see a video explaining circular motion a bit more.
In uniform circular motion, an object travels around a circle at a constant speed. The velocity of the object is the rate of change of position with respect to time. This velocity can be estimated by examining the change in position over a short time interval. The instantaneous velocity is then the limit of this estimate as the length of the short time interval goes to 0. Note that the direction of the velocity vector is always tangent to the circle. The acceleration of the object is the rate of change of velocity with respect to time. The acceleration of the object can be estimated by looking at the change in velocity over a short interval of time. The instantaneous acceleration is then the limit of this estimate as the length of the short time interval goes to 0. Note that the direction of the acceleration vector is always towards the center of the circle. The magnitude of the acceleration can be determined by noting that over a short time interval, the change in the position vector and the change in the velocity vector form similar isosceles triangles. This information then leads to a simple expression for the instantaneous acceleration and the limit as the length of the time interval goes to 0.